The selection of materials for optical components and thin films depends on the desired wavelength range and the applications. If we think about the visible range, our most typical substrate material, silicon dioxide, it's in two forms: fused silica, which is amorphous, and this is often used for wafers and optical fibers. Silicon dioxide is also in a form of quartz, which is crystalline form of glass. It has a little bit higher refractive index and it's birefringent. The refractive index of silicon dioxide is already familiar to us, and typically the wavelength range it is used is approximately here. It is good for visible range and also for the applications of optical telecommunications. However, what is not shown in this figure is the absorption of silicon dioxide, which starts to be increasing in infrared wavelengths. Therefore, glass is not suitable material for infrared optics. For optical thin film components, we need materials with various refractive indices, both with lower refractive index than fused silica and higher refractive index. There's very few materials that have lower refractive index, and typically they are fluorides. For example, magnesium fluoride, refractive index of less than 1.4. The refractive index of magnesium fluoride has similar shape than fused silica. The refractive index is overall lower and typically it can be used in the same wavelength range. Towards the ultraviolet, absorption is heavily increasing in this material as well. As for the other properties, magnesium fluoride is sensitive to water. Coatings with magnesium fluoride needs to be often protected somehow. Other popular glasses are borosilicate glasses. They are much cheaper, easier to fabricate than fused silica. They cannot sustain so high temperatures than the silicon dioxide based glasses, but are often the base of many optical components due to their low cost. The high refractive index material can be some oxide or nitride material, and one of the most typical material is titanium dioxide. It has relatively high refractive index of more than 2, and also that material has several crystalline forms, and all of these have different properties in terms of refractive index and birefringence. The refractive index of titanium dioxide follows nicely the Tauch-Lorentz model. It has really low attenuation until the UV range, and below about 350 nanometers its absorption is increasing significantly, and simultaneously the refractive index is also growing. But refractive index is more than 2 for a very wide wavelength. Even higher indices are available if we take semiconductors into account, and two semiconductors are silicon and germanium. They have really high refractive index and they have a band gap at infrared wavelengths. Silicon has a band gap of around 1 micron. It has high refractive index at the infrared, but it's very lossy at UV and visible wavelength range. As we see, the refractive index of silicon is peaking up to 7 at UV range, and after about 1.1 micrometer, the absorption of silicon is very, very small, and it can be considered almost completely transparent material at this wavelength range. On the other hand, at shorter wavelengths, silicon is indirect bandgap semiconductor, and absorption is significant, which makes it a good material for optical detectors. Finally, we have metals, and metals can be noble like gold, silver, platinum, and optically the real part of the refractive index can be smaller than 1, which makes them good materials for plasmonic applications, as we'll see later on during this course. Also, their imaginary part is very large, and therefore all the metals are also really lossy. Some other metals can also be used in optical applications. Their real part of the refractive index is higher than 1, so they behave like most common materials, but their imaginary part is very big, and therefore they are heavily absorbing, and especially they are used in optical absorbers such as neutral density filters.